Alright, so here we're going to talk about lasers. Just a quick overview of what lasers are and how they work, and basically lasers in a nutshell. So lasers, we see them every day. They're around us all the time. Medical equipment, procedures, CD and DVD players, laser pointers, probably your mouse, barcode readers, printers, all these other things. So we have them everywhere, and we've seen them, but what are they? Laser is a device that emits an intense focused beam of light through the process called stimulated emission. Laser is actually an acronym that stands for Light Amplification by Stimulated Emissions of Radiation. We know what light is, we know what amplification means. I'll talk about stimulated emissions in a second, and radiation is basically light emitted by atoms, and I'll talk about that in a little bit too. So what's the difference between a light and a laser? A light is incoherent, so there's frequent and random changes of phases between photons. They don't really travel together in phase. Light has all the spectrum of wavelengths, the red, the green, the blue, even the UV and whatnot, stuff we don't see. And light diffuses. So basically, if you turn a flashlight on, it gets wider and dimmer the farther you are. A laser is different. So the photons in a laser move together in phase, as you can see in this picture here. And lasers are also monochromatic, which means there's only one wavelength. So that's something that we perceive as only one color. So you have a green laser or red laser. And it's also directional. So the photons are parallel and they follow the same direction. So a light beam gets wider and dimmer the farther you are, and a laser beam is more of a sharp focused point of light. So let's talk about radiation. So as I said, radiation is light emitted by an atom. And we also talked about light being a particle. This was part of the wave-particle duality. So we're treating light here as a particle and not necessarily as a wave. And what we said the particle of light was a photon, and the energy of the photon was Planck's constant times the frequency of that wave. So this is what happens if you remember from chemistry. We have these shell diagrams, and here there's the first shell, so to speak, that has the 2 electrons, and that has a certain level of energy for the electrons. Once you get into the outer shell, they have a different energy level here, and this is wherever the electron is where it's most stable. And in the world, we always want, stability in the atoms. Anyways, we want stability, we want to be comfortable, so the electrons want to be as comfortable as possible and as stable as possible for the atom to exist. So what happens is, if one of the electrons is struck by another photon, the electron will drop to a lower level to stabilize. So maybe this one will go down here. So when that happens, energy is given off, and it has to go off somewhere. So the energy that's given off, it's given off in a form of light, which, as I said, is a photon. And so the energy released is the same amount of energy, which is up here, as I said, Planck's constant times the frequency. So it's always the same frequency, and this is where we get the monochromatic property from. So that energy gain is given off as a photon, and now you have 2 photons, which and then it just keeps going, which is the basis really for the stimulated emission. So now we'll talk about stimulated emission. So what happens is, if a lot of atoms are excited, and this is what we call is a population inversion. So if you think about the energy levels as buildings in a floor, and the electrons are the people in it, what happens in a population inversion is everyone tries to go down to a certain floor, like they're picking their friends up to go to a party, or there's a fire drill and they're all heading towards one thing. So that what happens is, the atoms, they're already excited and they're hit by this photon, and that photon matches the difference between the energy levels of the atom, and so because the energy is released, this is caused by something else, and this is what's called stimulated emission. In regular light, it's spontaneous emission, and that's a little different because that happens without any external forces. So the external force here is the photon. And so what happens is the second photon will go out with the first photon. They're kind of like friends, so they'll go out together in phase, and they'll have the same frequency, as I said, due to what we figured out in the photoelectric effect here. The energy of the photon is Planck's constant times the frequency of the light. So this happens, and you have two photons going out hitting other atoms, and more energy is released. So it kind of causes this chain reaction amongst the atoms. So this is where the amplification comes in, is through that chain reaction. And so the amplification is then further enhanced by mirrors. And even though the chain effect is going off, putting in mirrors will enhance that effect because they're reflecting off and going back and hitting even more atoms, which also releases even more energy. And like I said, the energy is in the form of light. So you put mirrors on each side, and these are strategically placed mirrors to direct the light, and they're partially transparent, so it allows some of the photons to escape. And these photons, of course, as I said, they're in phase, so they're coherent. So they escape, and they are directional, and they have the same wavelength, as I explained before. So hence, this is where we get the laser. So here we talked about lasers being a sharp focused light that is in one spot. So we described that it was light. It was light due to radiation, which was the giving off of energy of the atom. And I described how it was amplified through stimulated emission and through strategically placed mirrors that only allowed certain photons that are in phase to come out. So that, in a nutshell, is lasers.